Welcome to Chemical Process Safety. This video is about designing ventilation systems. A good ventilation system is one possible safeguard against an airborne toxicant. But how do we know if the ventilation is good enough? As a chemical process safety engineer, you might be in charge of determining the required airflow rate needed for adequate ventilation. As with so many other things in chemical engineering, we can start by performing a good old material balance. Let's envision an enclosed space where there is some rate of toxicant entering the air. This could be evaporation from a spill or leaking from a vessel. We'll come back to this in more detail when we discuss source models, but for now let's just call this evolution rate QM with units of mass of toxicant per time and assume that it is steady. Next, we'll assume that the rate of fresh air entering the room is the ventilation rate QV in the units of volume per time. Unless something has gone horribly wrong, the incoming ventilation shouldn't have any toxicant in it already. Unless the pressure, volume, or temperature of the room changes in response to the addition of air, which is highly unlikely, an equal amount of air will have to leave the room as well. However, unlike the incoming air, this outgoing air will have some of the toxicant in it. If I wanted to make the math easy, I would apply the well-mixed assumption here, which allows us to say that the exiting composition is simply equal to the composition in the room. But well-mixed would represent the best case scenario, which is not the frame of mind that I want to be in when I'm designing a safety system. It's more realistic here to say that mixing is not perfect, and I'll do this by assigning a parameter k to indicate the non-ideal mixing factor. You can estimate the value of K by consulting table 314 in the textbook. You'll need to have a rough estimate of the concentration of toxicant in the room and also a qualitative description of the mixing, i.e. poor, average, good, or excellent. Next, recall the general balance equation for a non-reactive system. Accumulation is input minus output. I can express accumulation as volume times the rate of change of concentration. Input is simply QM, since I said there is no toxicant coming into the room with the fresh air. Output is K times the concentration in the room times the ventilation rate. Quickly double check that the units of all three terms in this equation are mass per time. If I assume steady state, the accumulation term can be set to 0. Now I can rearrange and solve for the concentration in the room. C in milligrams per meters cubed equals QM over K times QV. Again, beware of your units. Lastly, convert the concentration in milligrams per meters cubed to ppm using the conversion I derived in a previous video. The result is our ventilation equation. This can calculate the toxicant concentration in an enclosed area in ppm as a function of evolution rate, temperature, mixing coefficient, ventilation rate, pressure, and identity of the toxicant. In designing our ventilation system, we should solve for the value of ventilation rate that would keep the steady-state concentration of toxicant below a hazardous level, whatever we decide that level to be.